eventually developed something called glass design charts, about which I'm going to speak a few slides later. So the basic machine learning paradigm is as follows. So the broad machine learning can be divided into supervised, unsupervised, and reinforcement learning. And in supervised learning, you can have regression and classification. And in unsupervised, you can have clustering. So what is the difference between supervised and unsupervised learning? In supervised learning, you give the input and the output. And once you have the input and output, you are trying to train a model that will learn the input-output relationship. So you're trying to learn the underlying function. And once you learn this function, you want to give a particular, for a new input, what is going to be the output. That's what you're going to predict in regression. In classification, again, you have input, but the output is not going to be continuous. Rather, it's going to be labels, just like male, female, or metals, non-metals, or conductors, insulators, right? So all this, or gases, liquids, or liquids, solids. So these are all different classes. So you can have multiple classes, and then you give input features, and from this input features, you try to train a model that predicts the output features. And then again, for a new input feature, you try to predict what is going to be the output feature. So this is the basic idea of supervised learning, wherein there is a supervision of the computer or the machine from some human labels. Now in unsupervised methods, there is no labeling. You are just going to give the data, and from this data, the algorithm is going to figure out different classes, for example. And the example is clustering. For example, you have so many people attending this talk today. So you just give the features of all these people, and from the features, the algorithm automatically groups people into different groups, maybe in terms of the year that they are in, or in terms of their interests, or in terms of their branches, or things like that. It can even, depending on what features you give, the algorithm can even cluster based on the color of the shirt or dress or whatever people are wearing, right? And reinforcement learning is slightly different approach, wherein you have a carrot and stick policy. There is a reward for doing the right thing, and so you let the system learn. And this is how the ancient game of Go was learned by a computer, and computer learns to play chess and all of these things. This is from the idea of reinforcement learning, where there is a final goal. The goal is to win the game. So what should be the steps that I take to win the game? And there is a positive reinforcement for the right steps taken. Great. So if you're going to use machine learning, now that you have some idea about different algorithms that are present in machine learning, if you're going to use machine learning, there is a general heuristic that you have to use. So for example, you start always from linear regression, because you should always choose the simplest model. Then see if the model is accurate enough. If it's accurate enough, don't use a neural network, or don't use something that's very fancy, because you should always go for the simplest model possible. Now, if it's not accurate enough, just see the size of samples. If you have less than 10,000 samples, then go for things like random forest or support vector machine or extreme gradient boosted decision trees, that's XGBoost, etc. But if the samples are more than 10,000, then you can go for something called the neural network, right? But neural network is really data intensive. If you give it a lot of data, then it will perform well. But if you give less data, then it will not. And if you need uncertainty in your predictions, then you should go for something called Gaussian process regression. So I'm just giving out all these names because, this is like a heuristic. So if you are interested in solving some problem, then you can actually take the methods from here and then use it. My idea is to just get you at least familiarized with the names of different methods that are available. And these are the typical steps that are always associated with machine learning, for example. What is it? So first step is data set preparation, wherein you clean the data, impute the missing data, remove outliers, etc. Then you prepare a training and testing data set. So you have a data set that's called a training data set. It should be representative of the major features that I said, like I gave the example earlier. Then you can try to reduce the dimensionality of the problem. For example, if you are giving some unnecessary variable, then you can remove the unnecessary variables and keep only the important variables. And then try to identify the appropriate mathematical model, like the one that I said earlier, depending on the size and nature of data. Then you train, validate, and test your model. And finally, you perform hyperparametric optimization to simplify the model and increase its interpretability. So these are the general steps that you have to follow whenever you are developing a machine learning model. And the last step of hyperparametric optimization is a very, very important step. Let me just try to give you some examples. So linear regression is something that you all are familiar with. The idea of linear regression is you have a few points, you try to fit a straight line to this. But how do you fit a straight line to this? You come up with a error function like residual sum of squares. What is residual sum of squares? It's nothing but the predicted value minus the actual value for the y feature. That means y predicted minus y actual and the whole square, and then you just sum it. That's the residual sum of squares. And whatever is the line that minimizes the residual sum of square, you say that's the best fit. So how do you start? You start from a horizontal line, see what the error is. If the error is high, you start reducing the error. Then you start tilting the line, so the error again reduces, and you just keep on doing this until the error becomes low enough. And then after this, if you again start tilting, the error starts to increase further. So you will see a U-shaped curve, and the minimum of U-shaped curve is what you will choose for linear regression. And there are some other approaches called lasso and elastic net, which will actually try to reduce the effect of outliers like this. For example, the point that you have here is an outlier because almost all the points are along this line and just one point is outside. So it's most probably an outlier. We cannot say for sure, but most probably. So this kind of approaches like lasso and elastic net will try to reduce the effect of such outliers to your model fitting. And then there is this idea called random forest, in which you have multiple decision trees, and that's again used for classification and regression. And for example, you give a feature, and then you say if it's greater than this. If you give, let's say, for example, Young's modulus. If the Young's modulus is greater than this, it goes along this tree. If it's less than 50, then it goes along this tree. Then again, greater than 25, it goes along this tree. Less than 25, it goes along this tree. And similarly, you can just keep on dividing it, and at the final node, you have some results, and then you average it, and that's how you get the prediction from random forest. So you have multiple decision trees combined together, and that's why it's called a random forest. Trees combined together to form a forest. And finally, you have the famous neural network. It's also called as multi-layer perceptron. Basically, what you have in a neural network is you have an input, you have an output, and then multiple layers in between, right? So 1, 2, 3, 4, 5. So this is a hidden layer 1. Hidden layer 1 has 5 neurons, you can call it, or perceptrons. And similarly, you have hidden layer 2, which has again 5 neurons, and hidden layer 3, which has 4 neurons. And you basically send the input through this, output through this, and then the output always has again an error function. It tries to learn the weights of these neurons in such a way that the final output error is minimized. And that's basically the idea of neural network. So the weights are adjusted automatically in such a, not really automatically, but using some algorithm. So there is an algorithm called backpropagation, wherein the error is propagated backwards, and then there is a gradient descent happening. Some magic is happening, and then you try to reduce the error. And whatever weights that minimizes the error is chosen as the weight of your neural network. Great. So I'm just going to skip how to design a neural network, but for those who are interested, they can contact me. I can give you the details, but generally the idea that I wanted to say is that you have an input, you have an output, and you try to reduce the error for the predicted output with respect to the actual output, and the weights are learned accordingly. Great. So now let's go towards the material design paradigm. So now that we are familiar with machine learning to a reasonable extent, let's see how this can be used for machine learning. What you do is that you take a data, you do data pre-processing, apply it for machine learning, do it for property prediction, and then develop something called material selection chart. Let me try to give you an insight of how we did it, for example, in glasses. Now, what are glasses? Glasses are essentially made of almost all the elements in the periodic table. So the easiest way to make a glass is you take beach sand, the sand that you get from the beach, you heat it to a very high temperature, maybe 1600 degrees Celsius or so. It becomes a molten liquid. You cool the liquid fast enough, it forms a glass. So all the glasses that you see around and the glasses through which you are seeing me right now is all made through this process. Now, the beauty of glasses is that you can take pretty much any element from the periodic table and put it in the liquid, and then you cool it fast enough, it all forms the glass. This raises an interesting question as to what is going to be the composition property relationship of glasses. Let's say if I have a little bit more oxygen, or if I have a little bit more boron, or if I have a little bit more sodium, how is it going to affect the property of glasses? And this question is not solved till date. And this is the question that we are trying to address here using machine learning. To do this, what we did is that we tried to predict the properties of glasses. So we took some of the common properties, that is density, Young's modulus, Vickers hardness, shear modulus, thermal expansion coefficient, glass transition temperature, liquidus temperature, and refractive index. So you can see the predictions from our model and the comparison with the experimental value. The x-axis is the experimental value and y-axis is our prediction. So there is a very good agreement for almost all the properties for the predicted values given by our neural networks, right? And you should remember that the input for this model is just the composition and output is the property of interest. So we are happy, great, neural network is doing good. So we try to actually look at how good it is doing. So for that, we try to look at a ternary. So this is SiO2, this is Na2O, this is B2O. So the color in the background actually shows the predicted value using our model, and the color in the foreground, the square dots in the foreground shows the experimental points. And what we see is that there is a very good agreement between the experimental points and the models for almost all properties, right? So you can see this is density, this is Young's modulus, hardness, shear modulus, thermal expansion coefficient, liquidus temperature, etc. Great. But then there is a problem for your neural networks, is that it's not able to predict uncertainty associated with the new predictions. And this is an important feature. To address this challenge, what we did is that we used something called scalable Gaussian process. So there is a special variety of this called KISS-GP. What is KISS-GP? It's kernel interpolation for scalable structured GP. And we use this again for all these properties. And what we observed is that our KISS-GP approach gave much improved results in comparison to the deep neural network. So if you look at it in terms of R-square value, you can see that for almost all the properties, the R-square value is greater than 1, and the accuracy for the model is very, very good. So that means you can actually use deep neural networks or Gaussian processes to predict all these properties: density, Young's modulus, hardness, shear modulus, thermal expansion coefficient, TG, liquidus temperature, refractive index, and bulk modulus of glasses. And from there, we developed something called glass selection charts, which is first of its kind. For example, it's like material selection chart by Ashby. So you have Young's modulus and density here. Why are we using this? If you want to have a glass with low Young's modulus and high density, right? So you should choose from these glasses. And if you want to have a glass with low density and high Young's modulus, then you should choose from here. And similarly, here is a graph for thermal expansion coefficient and Young's modulus. So these contour lines represent those lines are essentially E alpha equal to a constant. What is E alpha? Alpha is our coefficient of thermal expansion, and E alpha is nothing but the thermal stress developed for a unit change in temperature, right? Because thermal stress sigma is nothing but E alpha delta T. So if delta T is 1, E alpha is the thermal stress. In other words, the glasses along these lines will have exactly the same thermal stress when you change a unit degree change in the temperature. So you can see the Young's modulus can vary all the way from 200 to something like 20. And the thermal expansion coefficient can also vary all the way from 25 to 250. And you can have such wide variations in thermal expansion, but you can choose a glass from here and here. And that composite glass that you make will still not have any thermal stresses developed. And this is a very nice way of developing composite materials, new composite materials with multiple compositions and glasses combined together. We didn't stop there. We went ahead and tried to use different optimization algorithms like genetic algorithm, particle swarm optimization, and ant colony optimization to develop and design new glasses with targeted property. For example, you can see here the calcium aluminosilicate glasses with a target Young's modulus value of 80 GPa can actually be obtained by all this optimization algorithms. And a different family of glasses satisfying the criteria can be obtained using this optimization of glasses using different algorithms. From there, what we did is that, and this is going to be inspiring for all of you undergraduates who are and postgraduates who are interested in taking research from your laboratory to actually entrepreneurial activities. What we did is that we developed a software package called Piggy, Python for Glass Genomics, which is a machine learning tool to predict the composition property relationship and design optimized inorganic glasses. So this is actually available for everybody to use. I would recommend all of you to go to our webpage, piggy.iitd.ac.in, and you can just try out our software Python for Glass Genomics for free. And this work was actually featured by several news outlets, including the American Ceramic Society as first of its kind. And this is the framework. So once you go to the Piggy webpage, you can log in, and there are several modules. Piggy Bank is something, a database of composition property relationships. Piggy Seer is a prediction module, and Piggy Zen is an optimization module using the algorithms that I just mentioned. Now, great, we developed machine learning models and all those things. But the question is, as an engineer and as a scientist, what you're interested is in kind of interpreting these machine learning models. Can we actually do that? Because I showed you the structure of a neural network. It's a very complex structure. So you have some input, some output, and then a lot of neurons in between. Can you actually make sense of what is happening in the middle layers so that you can get some physical insights? We try to do this using something called Shapley additive explanations. So the idea of Shapley additive explanations is as follows: that let's say you give 3 input variables, age, gender, and job. Okay, and then you try to finally predict the salary as a function of your age, gender, and job. So you have a model for predicting salary. Now what you do is that you just don't give the input for gender and job, but just give only age and then see how the salary is changing. Similarly, give only gender and not age and job. See how the salary is changing for the model developed already. And similarly, give the third one. Now you start giving the combinations of 2, like give age and gender, age and job, and gender and job, and then finally all 3. So from this, you can actually understand the influence of each of the input variables like age, gender, and job on the output. And this idea is called Shapley additive explanations. So we actually try to use it to understand the importance of features. So here you can see different oxides that are used in our model, that is SiO2, TiO2, Nb2O5, etc., etc., etc. So you can see that SiO2 is going to be a very important feature controlling a Bay number. And you can see for each prediction how SiO2 is either increasing the Bay number or decreasing the Bay number. Similarly, this is true for all the oxide components. In other words, we can actually now interpret machine learning. So if anybody tells you that machine learning is actually a black box method, tell them no. Machine learning can actually be interpreted, and there are algorithms to interpret machine learning algorithms, and gives us precise information about what is actually happening within the machine learning model and allow us to understand the physics that's learned by the machine learning model. And this is going to be a crucial, important aspect going forward. Great. So I would like to show you something that we have developed from this called a glass veil. Now, what you have here is similar to our glass selection chart. This is an Abbe number refractive index plot. And you can see that the shaded regions that we are showing are actually the glasses that we have discovered, and the dotted regions are experimental points. So you can actually see that much beyond the experimental points, we have been able to come up with a lot of new glass compositions, and the components used in this are also given here in terms of the elements in the periodic table. Great. So here is the last topic that I want to slightly touch upon to just give you an idea of natural language processing and how this can be used to learn, to extract information. So far we spoke about machine learning for predicting compositions, composition property relationships, and classifications. But you see, most of the knowledge in literature is actually hidden in text. It will not be very nice data sets that you typically get, right? For example, if you want to learn for the exam, you actually read the text. You don't actually look at tables and just by heart the numbers in tables, right? And we try to emulate this process using natural language processing. So to this extent, what we did is that we downloaded like 100,000 papers, almost a million research articles, and then tried to learn what are the topics that are there in these research papers. And you can see actually, automatically this algorithm called LDA gave us the different topics from this, great 1 million research papers that we downloaded. This is luminescent studies, dielectric properties, spectroscopic property, radiation, thin films, all these different topics. And the beauty is that the algorithm actually tells you the distribution also. So which topic is maximum? It's clear thin films is one of the most studied topics. And similarly, you can see topic number 13 is also not bad. And topic number, then this is followed by other topics, right? So this actually gives you a holistic view of what is happening in the literature. In fact, we tried to do something more interesting. That is, there is really no way to search for images as of now in, from scientific literature, right? So what we try to do is that to solve this problem, we try to develop something called a caption cluster plot, which is nothing but a summary of all the captions that are present in literature. So here you can see the maximum studies in glass literature has happened on annealing. And then the second is XRD. And similarly, you can see there is atomic force microscopy, there is EDX, there is SEM, and all those different kind of topics are there. So this kind of actually gives you an easy way to search for images from scientific literature, which is not possible till date. Great. So with this, I hope I have given you a broad overview of what all can be done using machine learning and natural language processing and scientific knowledge extraction, etc. What I want to tell you is that you see there are many avenues for all of you. So AI and ML is going to be one of the critical areas that's going to change the way we see knowledge, change the way we see science, and change the way we perform science. So many people might tell you that AI is going to replace scientists. No, AI is not going to replace scientists. Scientists who use AI will replace those who do not. And with this, I would like to conclude my talk and then leave the stage open for any questions that you have. I would be happy to answer those. And once again, thank you, ASME and IIT Silchar, for giving me this opportunity to give a talk on AI and ML for materials discovery. Thank you.
So
Can
thank
you
you so
hear?
much. Students are requested to ask any questions if they have anything in their mind.
Good evening, sir.
Yeah, go ahead. Good evening.
Yes, sir. Sir, I wanted to ask, sir, is there any way to teach machines to make mistakes?
Okay, that's a very interesting question. What do you mean by making mistakes? Because machines
Sir, yes, sir. The reason I asked this because now during our online classes we are using simulators for the practicals. So we give the same data and we receive the same like output result. But while doing practically in the offline mode, there is a tendency to make errors, to have increased amount of errors. So is there any way to get that while using it online using simulators?
Right. So you should always remember that machines only learn the data that you give it, right? And the accuracy of the machine learning model is also going to be dependent on the accuracy of the data. So you give the machine wrong data, it will make mistakes. You give partially right data, it will also learn the partially right model and it will keep on making mistakes. Because in fact, making uh, mistakes is actually the easiest way, right? So you don't train a model well, then the model will make mistakes, right? Getting a right model is always the difficult one. Now, there is an interesting question wherein if you want to make a specific mistake that is pre-planned, if you want the machine to give a negative answer which is pre-planned. For example, it's like this: you are at home, but somebody comes to meet you, and you want the machine to say, "No, you are not there at home." Right? For example, that's a premeditated mistake. So the answer to this is that you can actually do that if you give the machine enough of training data to actually do this. And this is one of key areas which I have not touched upon, which is called ethical AI. So AI also raises a lot of questions about ethics and what is right, what is wrong. I'm not sure if you have heard of this, that uh, in natural language processing also this is a big issue, that you typically give Twitter feeds or other things for machine learning models, but these Twitter feeds have a lot of racism, lot of sexism, lot of misogyny, and lot of nepotism in all the text that's given. So actually the machine also learns this, right? And this is actually a problem because this is not a virtue that you want machine learning models to learn. So this is a topic, a very hot topic of discussion, where there are several people in Google, Facebook, and Microsoft, and all this involved. They are actually trying to challenge and address these questions. Several colleagues of mine at IIT Delhi have also contributed significantly to this topic, which is called as ethical AI. So this is a very hot topic, and the topic which is really open. Does that answer your question, Smriti?
Yes, sir. Thank you, sir.
Great, thank you. Any other questions?
Yes, sir.
Mm-hmm. Yes, Rishikesh, go ahead.
Yes, sir. Sir, this is just my personal thoughts, but I think, sir, most of us have at least one thought about it. Sir, you just said that the AI will not replace scientists, but the scientists who use AI will replace those who do not.
It's
But,
just on
sir,
a,
if they, yes, sir.
it's just on a lighter note because I use AI.
No, sir. Sir, my point was, since the AI is still in learning phase, so it cannot replace us just now. But at some point, if the AI learns all that we can teach it, won't our need be not won't be not be needed anymore? Like if a scientist is using AI and it has shared all the research paper and all the analytics and other things with the AI, and now the AI can run all the experiments by itself, won't there be no need of any scientists and other work personnel?
Yeah, so this is actually a very philosophical question, but I can give you a very simple answer to this, that we are not yet there. We will not be there anytime soon as well, because it's not just about algorithms. It's about several, it's about going a few steps beyond that. So of course we have all these nice movies like I Robot and all that, which is going to tell us that AI is going to replace humans. Okay, we don't know, we don't know where we will get there with this. So, but this is just a philosophical thought. But I can tell you, from the advancements that we are at this stage, it's going to be very challenging to reach that stage. And secondly, almost all the research in AI and ML is right now open source, right? So that way, the society is trying to actually combine and build things together so that it will actually advance the society. So I can tell you that AI we are very, very, very far away from the stage where AI is going to replace scientists. Maybe, I don't know, 100 years or 200 years down the line, what will happen, we don't know. But then the questions also are there, right? What are the questions to ask? Because the way we see the world is from human perspective, but the way robots see the world or the way AI sees the world will not be from human perspective. So the questions that they want to ask will also be different, right?
Yes, sir.
So I think you can rest assured, I don't think this is going to happen in your lifetime. Maybe in your grandkids' lifetime, who knows?
Yes, as I had also the same thoughts, sir, that it will actually take 100 or 150 years. I would be dead by that time.
Yeah. No, who knows? Maybe by that time we will come up with a system that will make you live longer.
Yes, sir. That is also quite possible.
Yeah. And there are
Thank
many
you, sir.
thoughts, right? Even consciousness, people are trying to just preserve consciousness. There is this question of who, who am I? So there is a very beautiful idea that's given that let's say your brain can be preserved and your body can be independently preserved. So whether your body is you or whether your brain is you.
Sir, it's just like a TV series I saw upload in which the mind is actually uploaded on the computer while the body is dead, and they are again trying to download the mind into another body so that the person can live,
Right.
and that with other
These
concepts.
are all actually philosophical questions, and there was a movie also based on this, which is called The Ship of Theseus. And there is this beautiful idea of Ship of Theseus, wherein if you keep on changing all the parts of a ship, and at some point you become, that the ship doesn't have any of the original parts with which the ship was built. So can you still call it a ship of Theseus, or is it not a ship of Theseus? So these are all philosophical questions that come along with AI and ML, and to which we don't have very clear answers. But I think these are all questions that we have to think about. We have to ponder, and let's see where the world takes us in future.
Yes, sir. Thank you, sir.
Great, thank you.
Any
Any
other
other?
questions, guys?
Sir,
Hello.
I
Okay, I'll take the question from the lady. I don't know who that is because
Oh,
so far guys have asked questions. So
Anjali Rameja.
good evening,
Sorry.
sir. Good evening, sir. I wanted to ask that you talked about language processing. So, in which there is the idea of taking out the information from the available papers.
right.
So, can we do it with the simple clustering algorithm, or do we need any other specific algorithm to dig out the information from the written documentation?
Okay, so this is a little more complex process than simple clustering because the question is that what is it that you want to extract first, right? So I can give you the details, but we have done that. For example, first of all, downloading papers itself is a big challenge. So we have downloaded almost 10 lakh papers, which is almost 1 million papers. And from this, we have used both clustering based approaches. So LDA, latent Dirichlet allocation, is a clustering based, is an unsupervised approach. So that is one algorithm that can be used for topic modeling. That means to understand what papers are from what topics. Similarly, there are several algorithms for automatic data extraction from tables. Then similarly, trying to learn relations and trying to learn question answers from data, etc. So all of these are different algorithms. So it's not just one click and you get an answer, but rather there are several steps involved in it. If you are interested in the details, I can give you specific papers which will talk about this.
Okay, thank you, sir.
Thank you. I think there was one more question, right?
yes, sir.
Yeah, Rahul, go ahead.
Sir, so machine learning does require a lot of processing power. So I just wanted to ask what kind of sir, hardware and the software that you use for your research. As curious.
Don't worry about it because these days you have Google Colab. So almost all the power that you need for most of these algorithms, you will be able to get it from Google Colab. Of course, at IIT Delhi here we have a supercomputer. It's a high performance computer that's dedicated for these kind of applications. But I always suggest people to use Colab because in today's world you will not be restricted by computational power. So so you should use Google Colab.
Yes, sir. Thank you, sir.
Great. Any other questions?
Good evening, sir.
Yeah.
Sir, recently I learned about the face recognition in the Azure. There it has a feature which can predict the human sentiments just by face matching. So I just wanted to, out of curiosity, I just wanted to know how it works.
Oh, okay. So pretty much any image-based algorithms works as follows. So you give an image, so every pixel of the image is read by the algorithm, and then it tries to find patterns in that pixel and then assigns it a label. So again, so you start with a neural network with some random weights, you give all the pixels as input. So it depends on what kind of algorithm you use. Typically, you can use convolutional neural network. So in that case, there are some convolution that's happening. But what it tries to learn is that what is the feature that all these combined pixels are representing, and what is the label associated with the feature. Now you can give different labels like sad, happy, smile, angry, all this. So then for each, if you give enough faces, so then it will try to learn, if it is like this, it is somehow happy. So there is a pattern for the pixels, and if it's like this, then it's sad, and so on and so forth. So if you give enough variance of a certain emotion, then it tries to learn from all these patterns and then predicts it when you give a new face. So this is the easiest way to explain it, but there is a lot of mathematics behind this. You should look into convolutional neural networks, and if you are interested more into this as to how a convolutional neural network works.
Thank you, sir.
Okay, great, thank you.
Yes, sir. I think all the students have got cleared with their doubts.
Great. So I think then we
Yes,
can
sir.
wrap up this session.
Okay, sir. Yes. On the behalf of ASME NIT SILCHAR Student Chapter, we extend our sincere thanks to Dr. Anoop Krishnan, sir, for sparing us time for his busy schedule, which made us acquire a huge knowledge. Once again, we thank you to the fullest, sir. You are overwhelmed with your presence. Thank
Great,
you so
thank
much, sir.
you. Yeah, great. Thank
Thank
you.
you, sir.
Thanks a lot. It's been a pleasure interacting with you all, and all the best wishes to all of you. And feel free to just interact with me at any point of time if you have any queries, questions. Just feel free to shoot an email to me at krishnan@iitd.ac.in. I'll be happy to answer. All the best wishes, and thank you, and see you. Bye.
Yes, sir. Definitely, sir. Thank you so much, sir.